All right, hi, everyone. How you doing? All right, so my name is Brian. I work for the math department. I'm also a programmer, and I'd like to call myself a cryptography enthusiast. So today I'm going to go over some of the basics of cryptography, which will lead you to some clues to get yourselves out of this maze. All right, so we're going to get started with just quickly how I got interested in cryptography, because some of you might have those same interests. I love stories with mystery and secrets. You guys? Yeah? That table does, yeah. All right. And so with that, cryptography and secrets, they kind of go hand in hand, especially since cryptography is all about sending message disguised so that nobody else can read it. Next would be computer programming. When I got into it, cryptography was very easy to learn, especially when you can program it, and you can do a lot of cool stuff with cryptography, as you'll see today, which I'll show you some programs. And then mathematics. Later, when I was in college, I started learning the mathematics behind some of the more complicated ones that they use online, like sending credit card numbers over the internet, things like that. So I wanted to go over two quick stories that I love telling. This one has to do with Mary, Queen of Scotland, and Queen Elizabeth I. Anyone know them? No? All right. You might have heard the story. So the short story is that Mary, Queen of Scotland, she came to England, and she technically had a claim to the throne of England, which Elizabeth was the queen of. And it comes down to a group of people in England wanted to put Mary on the throne and assassinate Elizabeth. So Mary and this group communicated by encrypting these messages. And these messages were encrypted. I kind of box it up there for you. All the letters of the alphabet were replaced with weird-looking symbols. So A looks like a circle. Z is a 9. I don't know. H is the infinity symbol. So when you see this message, it doesn't make any sense. But the problem with this plan, which they encrypted all the assassination plots with this type of encryption, is that it's like one of the easiest types to break. And at this point in time in history, it was really easy. So clearly, the Elizabeth's spies got a hold of them, decrypted it, told Elizabeth, and Mary got executed for it. All because she used an encryption technique that was very easy to break. And at that time, there were much harder ones. So if she had used a harder one, maybe Mary would have been queen and Elizabeth would have been killed. My other story I like is the Beal Ciphers. This one isn't well known, but it's one of those that has to do with buried treasure in the United States. So Thomas J. Beal was just some guy who gave a locked box to, let's call him a friend, at a hotel. And he says, in 10 years, if I don't come back, open this box and follow the instructions. So clearly I love the story because it has mystery and secrets. And in that box, there were 3 ciphers, just lists of numbers that looked exactly like this. Is actually the first cipher. Now, what it was is Thomas and some buddies found all this gold and silver and jewels, and he buried it in Virginia. And all of that information is buried in this cipher here. Now, this cipher tells the location of the treasure. Any idea if that's been encrypted? What do you guys think? Or decrypted? No, it hasn't. So it's been about 200 years. It still hasn't been decrypted. The greatest cryptanalysts had tried it. Doesn't work. So that is still a secret. Now, the second cipher tells what the treasure is. That's why we know that it's gold and silver, worth a couple million now. I think 60 million. So that's a lot of money. And we know it, and because this one was broken, people haven't stopped trying to break the first cipher. Now, the third one just tells all the family members of the people who buried the treasure, because if Thomas didn't show up in 10 years, they were supposed to distribute it to family members. Any idea if people are trying to decrypt this one? No, why would you? You want the money, right? You don't want to give it to other people. So yeah, this one hasn't been broken. And at this point, people think that it was probably a hoax, but, that's not fun. if it's a hoax. So I like that. I like to think that this is still true and that there's some treasure out there somewhere. And then what happened was, because people couldn't break it, they sent all these ciphers and put it in a pamphlet and then sold them. And so that's why we have all those ciphers today. All right. Now, you guys read The Maze Runner. How many? Lots? All right, good. So you know how they escape, right? And when I was reading it, I don't know if I'm supposed to give anything away, but when I was reading it, what they did was they had to do some stuff with the mazes, and I tried to picture what that was, and then kind of put it in terms of cryptography. I wanted to send secrets. How could I do that? And one thing that I could do is, if I wanted to send a secret to a friend, I could print these in a newspaper. And then when the friend gets it, he can cut them out. And then what they can do is, say I had a code word, and I wanted to send that code word. What I could do is, all those mazes, when I put them on top of each other, should spell something out. When, on their own, you couldn't tell. Now, anyone know that word? I mean, it's a morbid word, but I mean, in terms of the book. Anyone? It is a code word from the book. That's why I ended up making it like that. Now, you'll end up doing something like that today, but yours is much harder. This was easy, but yours is harder, and so you'll get that when we give you your clue at the end of this talk. Okay, so just kind of the introduction to cryptography. What I like to say is that I got two people, Alice and Bob, and they're secret agents, and they want to send a message to each other, and Alice wants to send this message. So Bob, my cover is blown, Alice. Some of you might not be able to see the bottom, but she signed her name Alice. Now, if she sends that message and someone gets it, then not only is Alice's cover blown, but so is Bob's. So what she does is she encrypts the message. Oh, by the way, this is called plain text. Plain text just means that it's readable. All right. So she encrypts the message, and we call that the ciphertext. And if you look at it, it looks like gibberish, so you know something's up, but you may not know how to break it. So what she ends up doing is she sends off the message to Bob. Now, when doing cryptography, you must always assume that there is a bad guy that's trying to break your message. And so she also gets a copy of this. Now, they both open the message. They both get the gibberish, but Bob's the only one with the key, which we're going to talk about a little bit later on how you use keys to decrypt this. So Bob can decrypt it, right? And then he gets the original message, so he knows to run, whereas our enemy, all in black here, her name's Eve, by the way. So you got Alice, Bob, and Eve. Eve's for eavesdropper. Not a very clever name, but that's the names we use. All right, so then how did she encrypt this message? And this is the encryption technique you will be using today, which is called the Caesar cipher. It's one of the easiest ciphers and one of the earliest known ciphers, and Julius Caesar was known to use this. So I'm just going to talk about how this one works. So you have the plain text alphabet. That's our normal alphabet. He didn't use English. But if you take our alphabet, there you go, and then we have the ciphertext alphabet. The ciphertext alphabet is what all of our letters are going to get turned into. So if you go back to the Mary and Queen Elizabeth plot, the ciphertext were all those weird symbols, the triangles, the circles, all that stuff. Now, the way that the Caesar cipher works is, let me zoom in on this. You can see how A gets sent to D, B gets sent to E, and you're actually going to do that for all the letters of the alphabet. So what do you think C is going to go to? F and D, G, and so on, right? All right, so if you keep this up, all right, now at the end of the alphabet, W goes to Z. So where do you think X is going? A. So it's going to wrap around, and so does Y and Z. They wrap around to B and C. So that's how the Caesar cipher works. All right, you see how we have all these squiggly lines here? That's kind of annoying, especially if I want to change the shift. Meaning maybe I don't want to go to A to D, maybe I want to go A to M. It is very annoying to write all these lines out. So what you end up doing is writing the plain text alphabet in the top, and then the cipher on the bottom, and then just whatever you want A to go to, put it right below it. Right? So now this is much easier to read. Now, if I try encrypting Alice's message, what's B going to go to? E, right? All right, how about O? R, B goes back to E. What about R? U. And you'd keep this up until you had your complete encrypted message. Okay? Now, what you guys have is called a cipher wheel. All of you have them on your table. All right, so yours looks something like this. You got the nice logo in the middle. I didn't get the logo. But what I want you to do is that the outside of the circle is called the plain text alphabet, and the inside is the ciphertext. So again, Mary and Elizabeth's plot, that encryption, the inside here, where is it? This inside circle would have been all the weird symbols. And then the outside would have been, just the normal English language. All right, what I want you to do is with your pencil, mark a dot on the outside A. All right, now while you're doing that, the dot's there to help you keep track of your shift, okay? All right, which you can't quite see my A here, but I can move the A. What is A supposed to go to? D. So I moved A above D. Now, actually, I have numbers on that if you want, and it might be useful at some point during this presentation to start with the inside A and write a 0, and then go 1, 2, 3, all the way up to 25. That will help you with it'll definitely help you with your hint later on to get yourself out of the maze here. All right, so if I did a Caesar cipher, and you can see how A right here, let me zoom in on this for you. You can see how A goes to D, and B goes to E, and C goes to F. So we can start writing this out. What did you guys say B was? E. And then O was R, and you keep doing this, right? What was R again? U. U was X. Now, if you're interested in programming, I could do this by hand, but if you learn how to program, and you would do that, like some of your high schools even have programming, you can program your own version of this, and you can just have it automatically encrypt. So that's interesting. Now, if you try doing a different type of encryption, let's say A goes to E, then what's B go to? B goes to F. That's down to F. All right, how about O? O goes to K, right? And if I substitute this, that's not right. O went to S. Wow, I'm wrong. Okay, so O goes to S. Sorry, right there, O. All right, so you can actually see how, you guys see how this works then? Because you'll be encrypting your own stuff in a little bit. Good? All right. Okay, now let's suppose that Alice sends that same message and she encrypts it, but she doesn't tell you the key being the password, how to actually set up that circle. All right, so what would you do? What do you think you would do? Yeah, you would try a bunch. There's actually 26 different places that circle can move to. So there's really only 26, combinations you have to check. So let's go ahead and check those. All right, so I have my encrypted message up here. All right. Now, right now, if I actually go do a Caesar cipher, let's pretend like she did a Caesar cipher. You're starting from the inside, and you go out. So G, look for the G on the inside circle. What does it go out to? It goes out to D. How about T? T goes to Q, and G goes back to D, and you would keep this up. And when you're done, you would have that message, which doesn't make any sense, right? So that was not the right decryption. That wasn't the right key. Now this was a key shift of 3. So if I move this over 1, what's this shift? 4. If I went over here to, or I put A above K, that's a shift of 10. Okay, so that's the key. So if somebody wants to encrypt something and wants you to decrypt it, they would say, use the cipher wheel with a key of 10, and that would set you up to decrypt it. Now, being that, as a programmer, I like to take things that are hard, that's a tedious task, and to program it so that it will go through all the possibilities on its own. And the program that I wrote does this, and it checks all 26 possibilities, right? And you would look through them all. Do you know what shift it is? Can you see it? It is 5. So if I didn't know what the key was, I can try them all. It happens to be 5, and now I know the message. So Eve could have done this, and Eve could have now known the message, which means Alice and Bob would have been in trouble. All right. So here's what I want you to do. Here's some questions I want you to answer. Now, it's helpful if you read the book. If you didn't, try to pair up with somebody who did. Now, what I want you to do is answer the following questions at the top. When you get an answer, you're going to encrypt it using the shift that I told you. And in the first question, you do a shift to 22. All right. Now, for questions 3, 4, and 5, it goes backwards. So before you get started, question 3 says, how old is Thomas? You have an answer. That answer is the shift that decrypts this message over here. Okay? Now, when you are done, all right, when you are done, there are some computers set up over there. There you have one person from your team go enter in the codes. That's what it looks like. This is what I imagined the code screen looked like on the computer in the book. I might be wrong, but that's kind of what I thought it would look like. And so you have all these codes, and find your 5 code words and go to the computer and put them in. And when you do that, you will be given a hint, your first hint to get yourselves out of the maze. There's only really one thing else I wanted to say before the next expert comes up. The thing about the Caesar cipher is that there's only 26 different ways you could do it. So what they ended up doing is, you can see my original and substitution. If you press randomize, all right, does everyone see that there is no pattern to the ciphertext alphabet, the bottom right here, where it says DIG and all that? There's no pattern anymore. So if you encrypt something like that, instead of 25 different possibilities, there's 400 trillion possibilities, which it took how long? Like a half hour to do 25 possibilities? I mean, 400 trillion. To give you an idea of what that means, if you were to check 1 per second, that's still 12 million trillion years to do it. If you did 1 million per second, like a computer, which that's already tough, is that 12 million billion? Wait, 1,000 million billion, 12 trillion years. And if you were to do 1 billion per second, which I don't think is possible, you would still take 12 million years to do it. But it is still an extremely easy encryption to crack. And unfortunately, we don't have time for it, but if you write this down, you can look up frequency analysis for substitution to just show you what that thing would look like. It's a tool that takes your encrypted message, and you would add up all the letters of the alphabet, like how many times they show up. So which one shows up most often in this encrypted message? Z. And you know the most common letter of the alphabet? E. So if you look through this message, what do you think all the Z's are? E's. And you would keep that going. So what would take you 12 million years would take you maybe 20 minutes. All right, so that is the substitution ciphers. I hope you enjoyed your time encrypting and decrypting. So have fun with the rest of the day, and good luck escaping the maze.